Well, I've got my sketch started here. In order to get that revolved around x equals 1, I'm going to go ahead and draw that mirror image so we can get a better idea of what this thing looks like. Everything is circular, so I get a circle there, and then I can go ahead and draw in some dotted lines there. So I can see that I've got this bowl. It's open on the inside with these curved edges. Well, the fact that it's open on the inside means that I'm going to need washers. That is not the best looking washer, but I think I can do a better job drawing it off of my shape here. If I fill my thickness in, I can see that this thickness right here is in the y direction. So I've got these washers, everything in the y direction. I need everything, including those two functions, in terms of y. So let's start with y equals x squared. If I take a square root on both sides, I end up with x is equal to the square root of y. The second one is y equals radical x. I'm going to square both sides of this one, and I end up with x is equal to y squared. Square root of y looks like this, and y squared looks like that. Our next step is to figure out everything that we need for our washer volume formula. Now, if you haven't learned washers before, take a look at my video here. It'll step you all the way through it. So I definitely want to integrate with respect to y. So I'm going to go from my lowest y value, which is 0, and this point of intersection right here is at 1. So I'm going to integrate from 0 to 1. I need my outer radius squared minus the inner radius squared. And then I've got my dy here on the outside. Now I'm going to bring up a picture that gives us exactly what we need to figure out the outer radius. Now my outer radius is the distance between these two curves. In order to find that distance, I need to take rightmost minus leftmost. And leftmost, well, it was that square root of x, but square root of x is actually y squared. So as I put that radius together, it's going to be rightmost minus leftmost. Rightmost is going to be x equals 1 minus leftmost, but leftmost is y squared in terms of y. So we've got minus y squared. Let's do the same thing for our inner radius. That inner radius is again the distance between my axis of revolution and that curve. That curve was y equals x squared, but in terms of y, that curve is really the square root of y. I'm again going to do rightmost minus leftmost. Rightmost is still our axis of revolution in this case, and our leftmost is the radical y. So we get for that inner radius 1 minus the square root of y. Back into our volume formula, we've got the volume is equal to pi integral from 0 to 1. These are y values. Inside the parentheses, we're going to put our outer radius squared, which is here, minus our inner radius squared, those are both squared, which is here. So we get 1 minus y squared, all squared, minus that inner radius, which is 1 minus radical y, all squared, and then dy. Now my next step is to work through the algebra and the calculus, but if you're feeling confident, go ahead and fast forward to the end and get the answer. Let's work through the math. The first thing that I need to do is to square those quantities. So I need the formula for a plus b squared. As I square this, I get a squared plus 2 times their product plus the last one squared. Let's put this in our integral. So 0 to 1. I'm going to use square brackets here, and I'm going to go ahead and square out this first one. So a is equal to 1 here. So that's going to give me a 1 plus 2 times their product. So that's going to be 2 times 1 times negative y squared. So that's going to be minus 2y squared. And then the last one squared, y squared squared, is y to the 4th. Okay, now for that inner radius squared, I'm going to do the same thing. So I'm going to square that 1, I get 1. and then 2 times their product. So 2 times 1 times negative radical y. So that's going to be minus 2 radical y. And then the last one squared. Radical y squared is y. So I get plus a y. And then I've got my dy on the outside. Now I'm just about ready for my integral for a power rule, but let's go ahead and put everything in descending order. It just bugs me not to have them in descending order. And I'm also going to change this radical so it's got a 1/2 power instead. So we've got still the integral 0 to 1. And then I'm going to start with my y to the 4th. So y to the 4th is here, y to the 4th. Next power is 2, which is here, minus 2y squared. The next power is y, but I've got to distribute that negative, so minus y. And then I've got my square root. I'm going to distribute my negative, so I get plus 2. Instead of the square root, I'm going to call that a 1/2 power. And then I've got a 1 minus a 1. So those cancel. This is all of my integral, and I'm ready for my power rule. Let's put that power rule together. So we've got pi, and here comes my power rule. Y to the 4th becomes y to the 5th divided by 5. Minus 2y squared becomes 2y cubed divided by 3. Minus y becomes y squared divided by 2. And then I've got plus, leave a little room out in front here. I've got my y to the 1/2, but I need to add a 1, which is the same as 2 halves. That's going to become a 3/2 power, but I'm going to multiply by its reciprocal, which is a 2/3. Okay. And this is all evaluated from 0 to 1. I can clean up this right here, and this is 4/3 y to the 3/2. So if I cross that out, I think I'm ready to evaluate this. Evaluating, I've got pi. What I really need to do here is this antiderivative in the square brackets, evaluated at 1, minus the antiderivative evaluated at 0. Well, that's not bad, because as soon as I put zeros in, there's a y in every single term. So that just goes to 0. What I really need to do then is to replace all of those y's with a 1. So doing that, I've got pi, and then y to the 5th over 5. That's really 1 over 5 minus 2 over 3, again replacing y's with 1s, minus 1 over 2 plus 4/3. I'm going to put that right into my calculator, leaving the pi off because I really just want a fraction there. And I get from my fraction 11/30ths, so my answer is 11 pi 30ths. You are doing so great. Next up,